Hello, I'm Seema and welcome to part 15 of the chapter Haloalkanes and Haloarenes. In part 14, I told you about the nucleophilic substitution reaction when we were discussing the various reactions that haloalkanes and haloarenes show. Out of these, the first category was that of nucleophilic substitution reactions, which we had started studying. I told you what nucleophilic substitution is, where there is a nucleophile which attacks the haloalkane and it removes the halogen and therefore it substitutes the halogen atom. That's the reason why we call it nucleophilic substitution reaction. Substitution done by a nucleophile. And I told you, we took a few examples and I explained what generally a nucleophilic substitution reaction looks like and how the halogen which leaves the compound is known as the leaving group. And we took a few examples of these reactions. And I told you, in the next video, I'm going to tell you about the mechanism of this nucleophilic substitution reaction. Nucleophilic substitution reaction takes place in two ways. One is the nucleophilic, it follows two different orders of reaction. The first one is known as nucleophilic substitution 2 or SN2 or bimolecular, in which it follows a second order reaction, and the second category is where it follows the nucleophilic substitution unimolecular or SN1 mechanism. In other words, there are two ways how nucleophilic substitution reaction takes place, SN2 and SN1. In this video, I'm going to discuss the SN2 mechanism, and in the next video, we'll go to the SN1 mechanism. So, the topic, therefore, of this video is the mechanism of substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular. On purpose, we changed the sequence. We would not normally in language say this because we would call it nucleophilic substitution or a bimolecular nucleophilic substitution, but we use this in this sequence because the formula that we write, or the the shorthand or the symbol that we use for such a mechanism is known as SN2. So for this SN2 mechanism or the bimolecular nucleophilic substitution, which is written as substitution nucleophilic bimolecular according to the formula, that is the mechanism that we are going to understand. The SN2 mechanism follows a bimolecular, that is, it follows a second order reaction, or it follows second order kinetics. Now, you've studied chemical kinetics. And what is a second order reaction? A reaction in which the rate of the reaction depends on two of the reactants, or on the concentrations of two of the reactants, and not on just one. That is known as a bimolecular or a second order reaction. So this is a mechanism, it follows the second order kinetics. It means the rate of this reaction depends on the concentration of two reactants. That is, the rate depends on the concentration of both the reactants. Since in nucleophilic substitution reaction there are only two reactants, therefore the rate of this reaction depends on the concentration of both the reactants. But in SN1 mechanism, it would be a first order reaction in which the rate of the reaction would depend only on one of the reactants, and that reaction would take place in two steps. Do you remember when we did chemical kinetics and we were understanding the rates of reactions? We understood that when you have a reaction that takes place in multiple steps, that step which is the slowest is the rate determining step, and the order of that step becomes the order of the reaction. So in the SN1 mechanism, you will have two steps, out of which one step will be the slower step, and that would be the rate determining step, and the concentration or the order of that step, order of reaction of that particular step would be the overall order of the reaction. We'll come to that in the next video. Let us now focus on the SN2 mechanism. Now, in this nucleophilic substitution, how is it that both the species, the rate of the reaction will depend on the concentration of both the species, which means that this reaction will take place in a kind of a single step. Both the reactants will react together and result in the formation. They will react, they will mingle with each other, whatever they would do, and it would result, the final product would be the product that you want, that is the substituted haloalkane. So in this you have a nucleophile, for example you have OH negative, which reacts with CH3Cl methyl chloride, and it gives you a transition state, a state in between. And what happens in this? The nucleophile comes and attacks the delta positive. You know, I told you that the chlorine or the halogen gives a partial negative charge to the haloalkane, and the carbon becomes partially positively charged. Therefore, the OH negative, the nucleophile, attacks the partially positive carbon. And when it attacks the a partially positive carbon, an intermediate state, now it is as if, you go out in the park, you move with your friend, and you're friends with one person. And all of a sudden there is another person in the park who's also playing and wants to be friends with you. So this person is coming close to you and you are getting attracted to this person because you feel that I could be better friends. This person is playing the game that I like more, and this one doesn't play the game that I like as much. But yet I'm with him because I did not have any other friend. So you're just holding on. While this one comes close to you, your attention goes away from the other friend you moved in with. So your friendship becomes a little weaker here already. There's a little doubt being created here. While your interest on this side is going on increasing. So a bond is being formed on that side, and the bond on this side is becoming weaker. And this is a state, this is the transition state. The previous bond has not been broken yet, and the new bond has not been totally formed yet, but the interest is on both the sides. Here it is losing interest, and here it is gaining interest. So that is the situation that is created, The nucleophile comes in, and the halogen, it starts losing its attraction. Therefore, the halogen starts moving away, which is the leaving group starts leaving, and the nucleophile starts forming its bond, resulting in the formation of a transition state. This transition state is very unstable. It is formed during the reaction, but if you imagine that, okay, let us get this species out, let us stop the reaction at this time and get this particular species, you will not get it. Because this is a kind of all this happens in a flow. It's a flow. You came into the park, you will never have that situation where you could take all three of you playing the two games together. So with this person, let us say you were playing badminton, with the other one you liked playing cricket. So it's not possible that you play badminton and cricket at the same time with both of them. So you cannot separate the whole species, the transition state. But finally, that one will go away and you will be playing cricket, maybe the game of your choice. So this transition state is only a transition state. You cannot separate the component from this state, the component in this state. And then it smoothly flows over where the leaving group leaves as the ion, that is the chloride ion, and you get the nucleophilic substituted product. That is the methanol. This is diagrammatically shown, the same thing. And the same thing is shown diagrammatically for a certain reason. Look, if you imagine that this is the carbon, this is chlorine, this is carbon, it has three hydrogens, I'm making the same. This is oxygen and this is hydrogen. Oxygen and carbon are going to get attached, right? So as this comes closer, they are electrons. Every bond pair is a pair of electrons. So you have these hydrogens forming a kind of a network in this direction. And when this oxygen comes close, it brings its own pair of electrons, and these two are also a pair of electrons. So more and more electrons are coming to this side. So too many electrons are getting collected on this side of the oxygen, which leads to a kind of a repulsion. Due to the repulsion of these, each one is an electron pair, each bond is an electron pair, and each atom has its own electrons. Since these are hydrogens, that is the only electron with each hydrogen, and the three electron pairs are present, and the electron pair here. So when OH negative and the negatively charged one electron it has, when they come, there is a repulsion of the electrons. And as a result of this repulsion, what happens is that these three bonds, they are pushed. What is a bond? It's a shared pair of electrons. It's nothing but electrons. So this pair of electrons is pushed by that pair which is coming in. And when it is pushed due to the repulsion, oh my God, it's like you're standing at the door of a bus and the bus is really crowded and one more person just jumps into the moving bus. What do? You're already at the door. You just step back a little, oh God, there's another person in the bus. So it is somewhat like that. One more, it's cluttering of electrons. So these three bonds, they have to move back to make space for that oxygen that has come in with its electrons. And as a result of this movement of electrons, the hydrogen nuclei are of course moving with the electron, because the negative charge, if it moves, the positively charged nucleus automatically is so attractive to the electron that it is definitely going to move. As a result, what happens? These electrons, they move away, the three hydrogens move away. And if in a tetrahedral shape, you would have 4 bonds in a tetrahedral. If this was carbon, the center was carbon. Now, this was how the molecule was. This was the halogen, the chlorine, and these three were the hydrogens. As soon as the oxygen came in from here, these 3 bonds were pushed behind. They were pushed, this became loose and this started coming away. Okay, this became loose in the transition state, and these 3 bonds, they kind of were pushed by the electrons coming in this direction. So do you see? Here you find that the bonds of the 3 carbon hydrogen bonds, they are kind of pushed away and they form a kind of a triangle here. And this chlorine which is present here, now it starts moving away. When it moves away, leaving as Cl negative, now the repulsion comes into play in such a way. Now as this moves away and you have electrons coming from here, why would they stay flat? They would form a tetrahedron in the other direction. Why would they not form a tetrahedral shape in that? That is what happens. So as the chlorine moves away, the tetrahedron which was in this direction is now made in the opposite direction. This is called the inversion of configuration. The configuration, the tetrahedral bonds were in one direction, they were all pointing this way, but as the electrons came, the oxygen with its electrons came, it was pushed in the transition state to the center, and when the chlorine left, they moved back to form the tetrahedron in that direction. Thereby, you will feel as if the umbrella was on this side and wind came and the umbrella was pushed backwards, like the inversion of an umbrella. I got my umbrella here too. So this is the chlorine atom here on this side. Okay, and as the umbrella, the bonds, the three hydrogens were in this direction, and then came the OH. And when OH came, these electrons started pushing the umbrella backwards. And when it started pushing the umbrella backwards, as if wind pushes it backwards, there is an inversion of the entire configuration. Now, the bond here is there, but you can't see the chlorine behind it. The chlorine has left. The chlorine that was attached on that side is no more there, and now in the end you get an inverted umbrella or the inverted configuration, right? So that is what appears to be happening when you have the SN2 mechanism. This is a very important thing to remember in the SN2 mechanism, that it leads to the inversion of configuration when the SN2 mechanism takes place. So what is important to remember about the SN2 mechanism? It follows the second order kinetics. So it's a second order reaction. It takes place in a single step, which involves the existence of a transition state. But that transition state is not stable, so you would not call it 2 steps. It is a single step, it's a continuous step. Only in between this stage is coming. Then, the second important thing about SN2 mechanism is that it leads to the inversion of the configuration. The incoming nucleophile causes a break in the carbon halide bond. The incoming nucleophile, it causes a break in the carbon and the halide bond. It causes a break in it, while simultaneously forming a carbon OH bond. So it's causing the break, but at the same time it is forming a new bond between carbon and oxygen. So one bond weakens, this bond is weakening and this bond is building. One friendship is going weak, one friendship is becoming stronger. So one bond weakens and one builds. As this happens, the configuration of the carbon, it inverts. The CH3, the three bonds of the tetrahedral figure that were pointing the three CH bonds, they get inverted in the end in the product. This transition state is unstable and cannot be isolated. I already told you this. It is now time to understand on what does this SN2 mechanism depend on, or which species would undergo the SN2 mechanism, and what is the reason, or which would be faster in doing it. So let us understand the preference in the case of SN2 mechanism. Now this reaction involves the attack of the oxygen on the carbon while simultaneously the leaving of the halogen atom, right? So if these three atoms, they were hydrogens, then that would be the easiest because hydrogen is a very small atom. Imagine if these were methyl groups. If one of them was a methyl group, then the repulsion would be even greater. Why? Because the carbon, this would be carbon instead of hydrogen, and it would further have three hydrogens. And this oxygen has to come and attack this carbon. So as the groups which are attached to that carbon, the alpha carbon which the oxygen is going to attack or the nucleophile is going to attack, as that carbon is attached to more and more bulkier groups, the rush at the door of the bus is going on increasing. Imagine if this was not just three people, they were women standing with, one standing with a dog, one standing with a cat, one standing with a baby in her arm, and then that person jumps up. That would be even more difficult for that person to jump up on a bus where not just three people are standing, it's already crowded, but each one has something in their arms. Plus maybe not just a cat or a dog, but a big bag, a hold doll or something, a huge purse, lots of stuff on them. So the bulkier these groups are, the more difficult it is for the nucleophile to attack the alpha carbon. So any species which has such bulky groups attached to the carbon atom, that species would not undergo SN2 mechanism that readily. It would not happily undergo the SN2 mechanism. So let us understand. Since the reaction requires the approach of the nucleophile to the carbon-bearing leaving group, let me repeat this. Since the reaction requires the approach, it requires the approach, that is the nucleophile is coming. It requires the approach of the nucleophile to the carbon which is bearing the leaving group, since this reaction involves the approach of the nucleophile and the presence of bulky substituents near this carbon, the presence of huge substituents near this carbon, the carbon atom will have a dramatic inhibiting effect. Inhibiting means when you are trying to jump up on a bus that is already full and which is moving, would you like to jump up on a bus where are three thin men standing, or would you like to jump up, stuff yourself into that doorway in which there are three women standing with, or men, whoever, standing with kids, dogs, cats, prams, hall dolls, purses? You won't want that. So the bulkier the groups that are present, that bulky group has an inhibiting. It is kind of inhibiting means it is a stopping. It stops that. It is a hindrance. It does not allow the nucleophile to attack so easily. It is discouraging. Inhibiting is kind of a discouraging effect. So it has a dramatic inhibiting effect. Therefore, methyl halides will react most rapidly. Methyl group would react the fastest. Why? Because it has the smallest of the groups attached to the carbon, that is hydrogen. Hydrogen, when you use the electron in the bond, it is only the nucleus of hydrogen with one little proton which is present. So it is the smallest possible group that could be there. So methyl halides would undergo nucleophilic substitution very happily because they do not have bulky groups. So methyl halides react most rapidly in the SN2 reactions, and the tertiary halides on the other hand would react the least. So I've made the structures for you to understand how the bulk of the groups affects. Now nucleophile has to attack this carbon. It has only 3 hydrogens, and hydrogens are small. It is easy. It's the easiest. In the case of ethyl group, this is the alpha carbon to which the halogen is attached. And a methyl group, one of the groups, these 2 are hydrogens, but one of these is like a bigger ball, like a bigger, what should I say, a bulkier group. So if you imagine them to be small balls, these are like small thermocol balls, and this is like a tennis ball all of a sudden. So the nucleophile, when it comes, it gets lesser space. In space, it has lesser space to jump into the bus. So this would undergo SN2 mechanism a little less readily. Then comes the isopropyl or 2-degree methyl halide, also alkyl halide, so not methyl halide. Now this is isopropyl halide. So in this you have one carbon attached to 2 other carbon atoms, which means it is a 2-degree halide. This is secondary halide. And the nucleophile has to attack now. There is only one hydrogen, and these 2 are tennis balls, and there is only one small little thermocol ball. So it becomes even more difficult. And in the case of a tertiary butyl halide, which is tertiary, you have 3 methyl groups. The carbon is attached to 3 big tennis balls, and the nucleophile actually finds no space to enter. Where does it enter from? The poor nucleophile has to go in. There's a tennis ball here, tennis ball here, tennis ball here, and all of them pointing this way because it was a tetrahedron. They are not straight. They're kind of already clamored there. So spatially it is difficult for the tertiary the tertiary alcohol to undergo nucleophilic substitution by bimolecular or SN2 mechanism. Then if you had the same alkyl group, let us say we have just methyl group, but the halogens are different. Does the presence of a different halogen for the same alkyl group also affect the rate at which the nucleophilic substitution or the readiness with which the nucleophilic substitution will take place? Of course it will. We know that iodine has the largest size, then comes bromine, then chlorine, and the smallest size is of fluorine. So when iodine forms a bond with the carbon, with the alpha carbon, that bond is the longest bond because iodine is large in size. Its nucleus is further away. And therefore breaking this bond is the easiest. Then comes bromine, which is slightly smaller, and the smallest is fluorine. So if fluorine is the smallest, the 2 nuclei are very close. The friendship is really fast. They're kind of close friends. You can't break them apart. So this mechanism, the rate of the reaction or the readiness with which SN2 mechanism would take place would be the best. Ri or iodine would be the best leaving group, we could say. Bromine lesser than that, chlorine even lesser, and fluorine would not happily leave. So that is the order in which this SN2 mechanism would take place. Now let us do one solved example of your textbook before I wind up this video. Give me a moment. Okay, this is example 10.6, the solved example of your textbook. It says in the following pairs of halogen compounds, which would undergo SN2 faster. Now that you have understood what SN2 is, and you've understood what are the factors that determine, what are the 2 factors that determine how fast the SN2 mechanism will take place. One is the hindrance caused or the inhibition caused by bulkier groups. More the bulkier groups, the slower will be the reaction. And the second is which group is a better leaving group. So these 2 examples are actually one example of each. The first one is you have cyclohexane, and to which CH2Cl is attached. And here you have the chlorine attached directly to the cyclohexane, to the carbon of the cyclohexane. Now this carbon here is attached, this is the alpha carbon here in this case. The The alpha carbon is sp3 hybridized, of course, and it is attached to 2 hydrogens and 1 chlorohexane and another carbon. And here this carbon or the alpha carbon is attached to 2 other carbons and with hydrogens, of course. This would be H, this would be H2, this would be H2. So this has bulkier groups attached to it. And this one has 2 hydrogens and only 1 bulky group attached to it. Right? So which one do you think would undergo SN2 faster? This one. Because in this, the alpha carbon is attached to 2 hydrogens and less bulky groups. And if you look at the second example here, you have iodine and chlorine, and otherwise the compound is the same. So this is CH3, CH2, 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 iodine, right? So it is butane or iodobutane, and this is chlorobutane. So in iodine, what is the difference between the two? One is the difference is only of the halogen. One is iodine, the other is chlorine. Iodine, being the larger atom, is a better leaving group. Therefore, this is the one that would undergo SN2 faster. Here also, this is the one that would undergo SN2 faster. So this was example 10.6. And with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.